In some of the recent videos, I've made some vague references to inadmissibility as one way to choose between different estimators when you don't want to assume or you can't assume a prior. And inadmissibility is a way to reject certain estimators. So it gives you a clear-cut way, certain conditions under which you can clearly say that's a bad estimator. So to introduce inadmissibility, first recall the definition of the risk function, a function of theta and delta, a decision rule delta, and a parameter theta. This is the so-called frequentist risk, and it's just the expected value of the loss function for some loss function on theta, the value of the parameter, and delta of the data given theta. So it's averaging over the randomness in delta. It's the expected value over with respect to delta. And let's look at a little example here to introduce admissibility. First, before we define it, let's just motivate the definition first. So we talked about a little example in one of the recent videos where we had a random variable x which was normally distributed with mean theta and variance 1. And let's take a look at the square loss, just theta minus theta squared. And we'll take our data. Let's say our data is just this single point x, so n equals 1. And in that little example, if you watch the other video, we had a natural estimator, which we called, it was sort of natural in some sense, delta 1 of the data, which was just x. And I should say this is an estimator of the mean theta if we want to estimate the mean. So this one was natural in some sense, at least according to our intuition. And then we had a silly estimator, delta 0, which was just identically 0. It just ignored the data altogether and said, I'm going to choose 0. And we calculated using the bias variance decomposition, we calculated that the MSE of delta 1, or I guess I could say, if we defined this, theta 1 hat of this, I'll just say delta 1 for now. The MSE of this was 1, and the MSE of this silly one was theta squared. That's just an easy calculation. If you didn't watch that, you could check that yourself if you want. And now let's draw what these look like. Actually, I guess I could have put here. I should have put maybe. So that is the MSE, but the MSE is also just the risk. The risk of where theta is the true parameter and delta is the procedure. So let's draw these as a function of theta. We've got, make that the theta axis. Theta is just now it's just a one-dimensional real number. And maybe this is see if I can draw, can I draw straight? There we go. Straight axis for the risk. And let's draw these. So the first let's draw the natural. I mean, that's just, well, it's just very simple. It's just equal to 1. It's identically equal to 1. So that's easy. We can just draw a straight line. And this is, I'll put it here, I guess. R of theta and delta 1. This is called the risk function for delta 1, a function of theta. Now let's draw the silly estimate. So this is the silly estimate, or the silly decision procedure. The silly decision procedure is just theta squared. The risk function is theta squared, so this is just a quadratic. Boom. Just like that. And this one is r of theta and delta 0. So now you might say, well, let's see. Let's think about if we wanted to have small risk. This one here is smaller for some thetas, in particular any theta that has absolute value greater than 1 is going to be this because this is 1 here, right, where they cross. So whenever theta is greater than 1, this is going to be smaller. But on the other hand, this is also smaller for some. This is all totally obvious, but I just want to make it very clear. Smaller for some theta. And it touches 0 there. So you can't say that this one is always better than this one. You might say, well, okay, but most of the time, the vast majority of the time, this delta 1, the natural estimate, the natural decision rule does better. And only this very small part, only a very small fraction of thetas does this one do better. But in order to make that sort of argument, you would have you're sort of implicitly assuming some prior, even some improper prior on theta. So in this case, it's not a clear-cut choice. On the other hand, if there were something else, like, maybe there's a third decision rule. Maybe it doesn't. Maybe it's always less than this one. Always less than delta 1, something like this. Delta 2, maybe. Then it would be clear. If this was always less than this, then you should never choose delta 1. You should always choose delta 2, because it's always going to give you a lower risk. Even though you don't know what theta is, remember, theta is some unknown parameter. Even though we don't know what theta is, we could choose this, and we would be guaranteed to always do better. So that is called. So when this happens, we say that delta 1 is inadmissible. So let's write down some definitions to formalize this. Given decision rules delta and delta prime, we say delta dominates delta prime if the risk function r of theta and delta is less or equal to the risk function r of theta and delta prime for every theta, every possible theta, and it's strictly greater for at least one theta, for some theta. So it's less or equal for every theta, and it's strictly less for at least one theta. And this is called, when this happens, we say that delta dominates delta prime. So in this case, delta 2 dominates delta 1. And now, I'm sure you can see where this is going. Now we have the definition of, let's make it a different color, inadmissible. And I'm sure you could guess what it's going to be. A decision rule delta is inadmissible if there is another decision rule that dominates it. Decision rule that dominates delta. So in this case, just like I said before, since delta 2 dominates delta 1, then delta 1 is inadmissible. So this is inadmissible, or rather, delta 1 is inadmissible. Otherwise, if it's not inadmissible, then we say it's admissible. So if there's no decision rule that dominates it, then it's admissible. And now here's an interesting fact. This is an interesting fact. Maybe a little surprising. So here's a fact. Both delta, so remember we had in our little example, we had delta 1 and delta 0. We had the natural decision rule and the silly decision rule. And it turns out that both delta 1 and delta 0 are admissible in this case of just a univariate Gaussian here. So both of these are admissible. So, in particular, the silly decision rule where we just pick 0 is admissible. There is no decision rule that always does better in the sense that it's better for every theta and strictly better for some, for at least one. So even though inadmissibility gives us a way to reject certain decision rules as being bad in some sense or unacceptable, it does not necessarily guarantee that, and a rule which is admissible is not necessarily guaranteed to be a good, in some sense, a good or sensible decision rule. And this is a perfect example of that, because this is just it's just an absurd decision rule. Why would you? I mean, that's just silly. Just saying 0 every time. So, and yet it is admissible.